And welcome back. Yeah, this is the third class in our course. Last class we talked about the way the energy balance, what is radioactivity, where does it come from? It comes from nuclei that are trying to release energy into the universe and become more bound and lighter. And that way we talked about what is radiation, exactly what is alpha radiation, what is beta radiation, gamma radiation, and all that. But we stopped there, right? So now we know all about, kidding, all about the energetics of this process, but we don't know much about how it happens. We know what happens, we don't know how. And this is the idea of this class. We're talking about the dynamics of radioactive decay. So, essentially, one important thing to know is a statistical and probabilistic process. What do I mean by this? I mean that the probability of a single nucleus decaying is independent of its chemical form, physical states, temperature, or pressure, and that the probability is equal and constant for any nucleus of a given time at any time. Meaning I have 10 nuclides here, exactly same nuclide. There's no way I can tell who will decay when, right? And the decay of any of these nuclides is completely independent of the decay of the others. But I know there's 50% any of this will decay in a given time. Say in 2 minutes, there's a 50% chance each one of these will decay. Meaning that if we have billions of nuclides in 2 minutes, half of them will have decayed and half will not. It also means that if I give just a small fraction of time, some of them will have decayed, right? Because it's independent, it's just a probability. If we take a look, we call this probability the decay constant here. It has units of the inverse of time, because essentially what it means is, what is the probability that this nucleus will decay in a given time? So the usual unit is per second, but it could be per day, per year, whatever. So what is written here, if you're not familiar with differential equations, what I'm saying is the ratio the number of nuclei decay with time divided by the number. So the number that decay divided by the total in a given amount of time is constant, right? As I told you, half of them will decay after some time, right? And then this here is just a measurement. The larger this number, the quicker the decay happens. It's easy to understand. Like I told you, right? This is per second. 1/2 meaning per second. So if there's a large number, that large chance it will decay per second means it will decay faster. If there's a very low chance it will decay per second, it will decay slower, right? This is what the decay constant is. It's a characteristic of any nuclide type that defines how fast or how slow does it decay, right? And if we take a look, just this is the differential equation. If I solve it, I don't know. Oh, if you're not familiar with differential equations, write this d here is like a delta. It's just a delta in a very small delta, but it means delta n over delta t. So the number of nucleons over the amount of time, just like a speed. And if I solve this differential equation, don't think you will do that. No need for that. It's just to show that, okay, this can be solved. And if we solve this differential equation, we come to an equation that said that the number of radioactive nuclei in a given sample at some point in time will be the number on t equals 0 times an exponential, e to the minus lambda t. What happens? What means this is we put here, this is an exponential, decreasing exponential function. It only means this is the form, right? It tends to 0 but never reaches 0, and there's a fact about it here. Well, there's always a certain amount of time in which it will decay by half. The number of atoms will decay by half. But then if I wait another time of this, it will decay by half again, right? Because that's the nature of the exponential. So here we had 10, we got down to 5, we got down to 2.5, we got down to 1.25, and so forth, okay? So it's a characteristic of this exponential equation is that there's always an interval in which it will be the number we have here will become half, and it doesn't depend on when is your t0, right? If I start counting here, wait this time, it will become half of this. If I started here, it will become half by here. At any point you start looking at some sample, if you wait some time, that amount of time, we call it half-life, half of those nuclides would have decayed, no matter if they were produced 1 year ago, yesterday, or just now. You wait one half-life, everything comes half of what it is. That's the nature of the exponential, right? And we have to define something. If we get this decay rate, meaning how many nuclides are decaying per second, we call it activity, right? And now we know that dn over dt is lambda n, right, from here. So activity is just the probability of emission times the number of nuclides. And now it starts to make sense, right? Because the larger the number of radioactive nuclides in a sample, the larger will be the activity of this sample, right? Makes sense. On the other hand, the larger the decay constant, it means the larger the decay probability of those nuclides, the larger will be the activity. Another thing that's important to know, you see, those are proportional, so the activity also decays with time with e to minus lambda t. So it follows the same rules as for the numbers. Meaning what? It also decays by half after a half-life. So if I had here 32 activity radioactive nuclides at some point, if I wait one half-life, they will become 16. And you have now 16 stable nuclei here, right? That were produced by the decay. I wait another half-life, we have now only 8 radioactive nuclides. Most of them are not radioactive anymore. And then if I wait, and so on, until the moment we have one. Won't talk about, because you see, these are billions, and then there's never one. But okay. Now, the present unit, the only thing that was important here, is to notice that at any point there's one half-life to when it will become half. And if I pass to another half-life, it will become half of that. And then it will become half of that other thing, okay? Always this. So, the present unit for this in the international system is the becquerel. Becquerel is 1 decay per second, right? This is the unit of activity you find. So, essentially what is activity is the number of decays per time. So, 1 becquerel is 1 decay per second. There's an old traditional unit that's still really used quite a lot around, especially when we talk nuclear medicine, sometimes also when we talk of applications in industry, is the Decay. You may have heard of it. It's the radiation emitted by 1 gram of radium-226. It's emitted, right? Mistake here. Meaning that if we take some counts, it is 3.7 times 10 to the 10th becquerel, right? 37 gigabecquerels, just to give you an idea, right? So it's much larger than the becquerel. That's mostly because why people still use it, but the international unit that should be used and we will use in this course is the becquerel. So half-life, as I told you about, the half-life is the speed with which an isotope decays, or more precisely, it's the time it takes for the number of particles to get to half of it, which is equivalent to saying it's the time it takes for the activity to get to the half, right? The half-life is a characteristic of the isotope. Each isotope has its own half-life. In fact, if each state on an isotope, excited states have their own half-lives, which are not the same as the half-lives of the fundamental state. And it may be of fractions of a microsecond to billions or trillions of years, right? So there's a wide array. We have things that decay in microseconds, nanoseconds, picoseconds. Typical radioisotopes we use on our daily routine, they can have a few minutes half-life, like 2.5 minutes for aluminum 28. They can be like I told you, technetium 99 metastable, which is 6 days. It can be 5 years for, as in cobalt 50, cobalt 60. It can be less than a year for cobalt 57. It can be 30 years as for cesium 137, and it could be 1 trillion years like in thorium 232. So you see, we have all this array of things, right? So we have here two examples. Iodine 131 has 8 days half-life, so it takes 8 days for it to go to half of its activity. Oxygen 15 takes 2 minutes to get to half of its activity, meaning that in 20 minutes it's 1,000 less times less active than it was to start with, right? While this one will take quite a lot longer. An example here, we have technetium 99 metastable, 6 hours half-life. Iodine 131, 8 days half-life. And cesium 137, 30 years half-life. So if we had 1,000 becquerels of each to start with, so by sunset you have 1,000 becquerels, right? 6 hours later you have, it's not sunset, it's okay, it's 2 o'clock in the afternoon. By the end of the day you have 500 becquerels. By very early in the noon you have 250, and then when day comes again you have 125 becquerels, so half, 1/4, 1/8 in 1 day, less than 1 day, okay? Oh, it's 1 day. So in 12 hours it goes to 1/4 of it, and in 24 hours it's 1/8 of what it was. No. If we talk iodine 131, it's a bit different. On April 12th you have 1,000 becquerels. Here it took 1 day for it to become 1/8 of what it was. For iodine it will take 8 days for it to become half. Another 8 days for it to become 1/4. And another 8 days for it to become, so almost 1 month to have it down to 1/4 of what it was, 1/8 of what it was. And cesium-137 has 30 years half-life, meaning it will take 30 years for it to get to half of this. So we were in 1962, we got to 1992, 2022, and 2052. So you see, it's 120 years for it to go from the way it was to 1/8 of it. Okay, then let's define half-life. The half-life is the time it takes for the number of particles to get to half of it, right? If you remember that this was the equation ruling the number of particles over time, we have that it will become, after one half-life, n will become n0/2, right? And so we just do the math here, divide both sides by n0, and in case you're not familiar, also the logarithm ln, which is the natural logarithm, is the inverse function of the exponential. So the logarithm of an exponential is just the function itself. And like we see here, the logarithm of an exponential is the function itself, right? So we do all this math. There's also some tricks of logarithms. The logarithm of a ratio is a difference of them. We do this math here. Trust me, it's correct, I think. And we come to the fact that the half-life is, if we put this lambda here, it is related to the constant, decay constant, which makes sense, right? The larger the decay constant, the smaller the half-life. It makes sense. The larger the decay constant, the greater the probability it will decay quickly, the lower the half-life. And here is just an approximation. If you don't have a calculator, this is approximately what ln of 2 is equal to. So how do we measure half-lives? Well, there's essentially two ways. The most obvious way, you get a sample, make it have a radioactive sample, you put in front of a detector, and you follow its decay. If you follow its decay, you just then fit it to an exponential function, and you have the half-life, right? Using this equation here, only with a here. So a is a0 e minus lambda t, and you have an exponential function. In case you don't have a software that can do exponential fitting for you, well, there's ways to do that on Origin. I don't know if you know it, Excel, but say you don't. There's a trick to do this quickly. If you do the log of ln of the activity, remember I told you the ln of a function is of an exponential is the function itself. So the ln of this will be just ln of e is 1, right? It will be just minus lambda t. So this becomes a straight line. It's a0 minus lambda t, or ln of a0 minus the ln of the activity is ln of a0 minus ln of lambda t, and then you linearize the function, and you can, by the, you see here, this is, you see a logarithm scale, it becomes a straight line, and you can determine the half-life, or in fact the decay constant, by the inclination of this too, okay, by doing this here, right? If this is true, then you have, when you apply the logarithm, you have ln of a0 minus lambda t, and then you have, okay, it's just a trick. If you have a software that can feed exponential functions, it's easier, but if you don't, this is a solution too. But then there's a problem. Okay, we are following the decay of the activity of a nuclide, but then say we have a nuclide with 1,000 years half-life, 1,000,000 years half-life. We will measure it for 1 year, and you will see no difference in the activity. So how can you determine the half-life of it? Well, if we remember that the activity is lambda n, meaning lambda is the activity over n, right? This is called specific activity, right? The activity per number of nuclei. Now, if we remember from chemistry, undergraduate school chemistry, mid-school chemistry, we remember the definition of the molar mass, which is the mass of one mole, meaning that the number of particles in a given sample is given by the ratio of masses times Avogadro's number, right? So if we do that, and once again this is just the definition of molar mass, we can substitute n here by this, and we get this equation here. So we can determine, if we measure the activity of a sample in a given time, we know the molar mass of that nuclide, we know the mass of that sample, and we know Avogadro's number, and then we get the decay constant, right? That's what we call the specific activity method. Very useful for very large half-lives. Not really useful for very short half-lives, though, because here it's implied that you're measuring the activity and the mass at the same time, which is not true. You don't have a scale on your detector. So there's a small difference here from the moment you determine the mass to the moment you determine the activity. For very short-lived nuclides, this correction is quite large, and the uncertainties involved start to overcome everything you've done. Okay, so long half-lives, we use the specific activity. Short half-lives, we just follow the decay. Okay, so to finish, let's take a look at another exercise here. So cobalt-57 is a radionuclide with a half-life of 272 days. First of all, determine its decay constant. How do we do that? It's easy, right? You have the half-life, you have the decay constant to the half-life. This is the relation, right? So we'll come to 10 to 2.95 times 10 to minus 8 seconds per second. So the probability each nucleus will decay in a second is 2.95 times 10 to the minus 8. Never mind here, something went off here. I'll talk about it when it comes. Then we say, okay, now if you have a radioactive source of cobalt-57 with an activity of 2 microcurie, how many radioactive nuclides does it contain? Once again, I told you we wouldn't use Curie, only becquerel, so it's only here to remember you of how you convert from one to the other in a test or in an exercise I give you. I will not ask you to do this conversion, right? You don't need to know that. It's just important you remember that Curie and becquerel can be translated one into another, like inches to millimeters or something. So here, just a small part, you have 2 microcurie. They are equivalent to 74,000 becquerels. Okay, nice. Now what we do, we have activity, we have decay constant, we want to know the number, right? So A equals lambda times n. So n is activity over lambda. Right, so that's it. And you have 2.51 times 10 to the 12 nuclei in that sample. Right? Just to give you an idea, this is much, much, much lower than the mass of 1 mole. If you remember that 1 mole is 6 times 10 to the 23. Right, so you're talking about very, very small samples, in fact. It may be strange to say that 1 trillion to quadrillion nuclei is, yeah, 2 trillion nuclei, or whatever. 2 trillion nuclei is just a handful, but it is, right? Nuclei are, atoms are such a small thing that anything we can think of have billions times more than that. So it's essentially, I could have put it here, just forgot. It's picograms or something, right? And so this, and then the question is, what will be the surface activity over 1 year? Let's start by not doing math and just taking a deep, see if we got the concepts right. The half-life is 272 days, which is less than 1 year, right? So what's your first guess for what will be the surface activity after 1 year? It's more than a half-life, so it should have decayed to less than the half of the original activity, right? Now we do the math and see if we got it right. This is the equation. Just put it in a calculator and you reach that it was, now it's less than 40% of the original activity, which is what we expected, right? Less than half. Meaning it's 0.8 microkehe. It was 2, now it's 0.8. And that's, you see, this is important to do, this step back and think, because sometimes we start to do math and calculate everything and we lose sight of more or less what we expect to find. And then we get to a very absurd number and we go on with it. No, if we have a way to have an estimative by heart, you should do that, because it helps you to check if your results make sense. Here's an important observation on half-lives, decay constants, and activity. In this exercise, if you take a look here, I converted the half-life to seconds. You don't have to do that, right? I don't do that when I'm working for myself, because if you remember, the half-life here was in days. So if I did all this, I would have, but there's one important part. If I used 272 days here, lambda would be in per day, day to the minus 1, not in second to the minus 1. There's nothing wrong with that, okay? What's the problem is when you use this equation here. In this, everything would be okay, right? But here there's a big problem. No, here it won't be okay either, sorry. Because every time you use this equation, this here has no dimension, right? It's just number. This here, the unit is per second, is becquerel. So this here must be per second too, otherwise things go wrong. So when doing decay analysis like this one, you don't have to have this up here. You can test yourself. If you use here, if you use 272 days here and determined here the lambda for in day to the minus 1 and put it here, the result will be exactly the same, which possibly less chance for error. But when you're talking about this equation here, activity related to a number of particles, you have to have the right unit here, otherwise your activity won't be in becquerel, it will be in something else. Okay, so this is important. If using half-lives or lambda in other units, you have to convert it to 1 over s, 1 per second, before determining the activity. Okay, this is important. So if you feel more comfortable, you can do every time the calculations in seconds, no problems. But just know it's not mandatory for decay analysis, but it's important for activity determination. Okay. Another question here. I'll let you follow this one up, but just to see. Now the idea is to know the mass of iodine-131 that correspond to a 100 becquerel activity. You see that is 10 to the minus 11 grams. So I told you it's very, very small amounts. Okay, and that is the end of this class. So now hopefully we know what radiation is, why is it emitted, and now we have an idea of how is it emitted, right? What comes next, you see next class. Thank you.